Recording in progress.
And even then I wonder. There's no audio on the Zoom? There's a lot of scratching. Your mic is up. Okay, this is better, right? Thank you. All right, folks. We're changing topics. We are moving on to recurrent neural networks. Again, for those of you who are paying attention, what was the last topic we covered? CNNs, thank you, right? We closed out. So we've gone through 3 major themes so far. Can you identify them? What are the themes we've gone through so far? Anybody? Jay, what are the 3 themes we've gone so far?
If you want.
Yeah, I know, but I'm just asking the people in class. Anyone want to take a guess? So can you shut your phone over there, please? Turn your phone upside down. Yeah. Yes.
Neural network and convolutional neural network, and I don't know what's the next.
So what is the first topic we covered? Before we did MLPs, we spoke about what a neural network was, what its capacity was, right? The basic concepts. The second thing was we looked at how you could train a neural network. We used multi-layer perceptrons as our fundamental unit. And then we moved on to scanning for patterns, which gave us convolutional neural networks. So 3 themes, we are on to theme number 4. And that is the theme of recurrence. So this is going to be a series of lectures where we will build on recurrence, but then we'll move on to something that is not recurrence, but it will still be part of the same topic. So here is the problem. There are many situations where we have to consider a series of inputs to produce an output, and the output too may be a series. For example, a situation like this. I give you a recording, and every time I give you the recording, it's exactly the same length, say half a second. And you must tell me if the recording contains the word welcome, right? So before you do this, as we know from homework 1, you're going to convert the recording into a sequence of feature vectors, spectral vectors. So your actual recording is going to look like this, almost an image. And you have to determine if the recording had the word welcome. Now, based on what you know so far, how would you classify it? How would you classify it? We spoke of just using an MLP. We also spoke of scanning for a pattern. But when do you actually provide the answer? After seeing the whole thing, right? So you have to analyze the entire sequence before you determine what was said. And the output is a single classification result. But then here's something more, a little more abstract. The Steelers, meanwhile, continue to struggle to make stops on defense. They've allowed an average 30 points a game, and have shown no signs of improving anytime soon. For anyone who follows the Pittsburgh Steelers, this is pretty much the theme every single year. We're miserable. So which sport are we speaking of? How did you know? Yeah, but they could have been, there are other teams which are not, also called Steelers, which are not football teams, right? You have to read the entire thing till you get to the, till you can determine what was said. Is this a positive sentiment or a negative sentiment? Are they happy about what's going on, or are they sad? That's definitely negative, right? And how long did you have to wait to figure this out? All the way till the end. So again, you have to read the entire thing. You have to analyze the entire thing before you make a decision. Now, something like investing on the stock market. The input is going to be a sequence of vectors. The vectors may comprise stock indices for various markets or individual stocks. You have to analyze this sequence of vectors one per day. And then you have to decide today if today is a day when it's worth investing in the market in general or in a specific set of stocks. Again, can you just take a decision arbitrarily just like that? You just go in and say, today I'm going to find this thing, it's called APQL, I'm going to invest in it. Is that how you would go about it? Yes or no? No. Okay, so what would you do?
Look at the history and try.
You would look at the history, right? You're going to have to look at what happened in the past, and based on what happened in the past, you have to take a decision on what you think the future behavior of any stock today is going to be. So the decision must be taken considering how things have fared over time. In each of these cases, you have a problem where you have to consider a sequence of inputs, input vectors, and produce one or more outputs. For example, if you're performing classification or if you're analyzing the Steelers, you would read the sentence and then have just one output. On the other hand, if you're a stock trader, you're going to have to make this prediction every single day. Is today a good day to be investing or not? And obviously, like every other problem, this is a function estimation problem. You can do it with neural networks. Now, before I continue, I just want to make us clarify something about the illustrations I will use. The pictures that we've used so far look like the figure to the left, although turned slightly sideways. I've shown you the entire row of units in every layer. So you'd have one layer of neurons connecting to another layer of neurons, connecting to a third layer of neurons, and so on. I'm going to turn the whole thing to the side, so I'll show them sideways, like I have in the figure to the right. So when you see something like this, each box actually represents an entire layer of neurons. When you look at an arrow, it's not a single connection. It's a full connection between one layer of neurons and the other layer of neurons. This is how it's always going to be. Do not get confused, right? So each box you can think of as a vector, a layer. Each arrow you can think of a weights matrix. Similarly, if I had a network which we're looking at two vectors of inputs to produce an output, like you had in homework 1, where you were looking at a vector and its context, the figure that we would have drawn in previously would look to the left, like the figure to the left, but now I'm going to draw it like the figure to the right. Or say, add something like this. Again, the point is I'm drawing the network's edge on so that you can actually, I can illustrate entire layers and collections of layers without drawing too many little circles and arrows. So is this making sense, the illustration? Okay. So back to the stock market prediction problem. To predict something, we must consider a series of stock values in the past. You're going to have to look at several days of inputs to decide whether today is a good day to be investing in the stock market. Now, based on everything that you have learned so far, how would you model this network? Anyone? Anyone on Zoom? What kind of network would you look at for this problem? Anybody?
Hello?
Please go ahead.
Okay, I think that maybe we can use a convolutional neural network.
Thank you very much. That's
So,
perfect. Yes, exactly the answer I was looking for, right? I could just be doing something like this. Look at today, look at everything in the past, and then on each day, I can just analyze today's and the prior day's inputs and take a decision on what's going to happen. Because after all, you're looking for trends, right? This is a convolutional network, a time delay neural network. Now, here there's a problem, right? Something that happens today. Suppose I have this network. How many days in the past is it looking into? 3, right? If something that happens today, for how many days is it going to continue influencing the predictions? Hmm? Pardon me?
Hard to say, probably relevant for a while.
But in my model, for how many days is it going?
4 days.
4 days, right? This is what I call, everybody see what we're talking about over here. This is a finite response network. So something that happens here today only affects the output for n days into the future. If you're looking at today and the past n days. So in this particular model, so let's say something happened on this day here. It's going to begin influencing predictions now, and the next day, and the next day, and the next day, and 4 days later, it stops having any influence on your predictions, right? So given this, is this good enough? How many days does an event influence the output in the stock market, influence the stock market? Yeah, Katrina?
We don't know.
You don't know. There are trends, right? Can anybody suggest? Do you have daily trends? Does yesterday predict today?
Yeah.
Right? Yes
Yeah.
or no, right? Something that's going up yesterday is very likely going up today. What about last week? Does last week predict today?
Yes.
What kind of patterns can you have?
All kinds of patterns.
I can tell you that if there were no transactions exactly 1 week ago, there will be no transactions today because it was a Sunday, right? Last week predicts this week. What about last month? Does that predict the trends?
Yes.
People begin, when do people go to the market? Right after they get their paychecks, right? You're going to have fortnightly and monthly trends. What about seasons? Are they seasonal trends? You know, every time the season rolls over, you go and buy yourself winter clothes because they have, or as soon as winter comes in, you go and buy summer clothes because they are there on sale. Now, what about annual trends? Things perk up every Thanksgiving. They go up every Christmas, right? So these trends can be very long term and they can be arbitrarily long term. Something like this is simply not going to cut it, right? The dependencies can be arbitrarily long. I mean, last Thanksgiving gives me a pretty good idea of how this Thanksgiving is going to be. But then the Thanksgiving before that also has some influence because I'm going to be looking at the trends over Thanksgivings and so on. So how long do you really want to be looking back when you make your prediction?
The entire.
All the way back to the start of time, right? Would a network like this work? What would a problem be?
A number of parameters.
Too many parameters, right? This is not going to work, right? I think we're out of time, 3 seconds. So Pokemon Moltres, is that how you pronounce it? Moltres?
Yes, I'm here.
Okay, what is the answer to the first question?
Yes, true.
Thank you. And second one, Pokemon Vulpix. Who's Pokemon Vulpix? I hope I pronounced that right. Pokemon Vulpix? No? Okay. Pokemon Chansey. What's the answer to the second one? Chansey?
True.
Thank you, right? Does have, okay. What do you think? Is the second statement true? No, right? Because that input at time t affects the output of the convolutional layer network, convolutional network, for only as long as the width of the kernel itself. Once the kernel is past that input, it's not going to be affecting the output at all. Whereas we really want something that has infinite response. Something that happens today should continue to have some influence on the predictions you make in the future all the way to the end of time. The influence may fade with time, but you still want it to keep influencing predictions all the way with time. And how can one do that? Here's a very simple technique. I can just say that the output today is a function of the output yesterday. So what happens then? Something that happens today is going to influence the output today. If there's no further input, that output is going to influence the prediction tomorrow, and that output is going to influence the prediction the next day, and so on. So a single input with no subsequent input at all is going to influence predictions forever, right? So something of this kind, where the output feeds back into the network, it's called a NARCS network. Stands for nonlinear autoregressive network with exogenous inputs. And NARCS networks operate something like this. On, say, day t, you're going to be making your predictions based on the input on day t and also the output at t minus 1. So which means that you're going to have to initialize the output on t on day minus 1, because that's going to begin influencing predictions on day 0, right? And then that output influences the prediction the next day and the next day and the next day and the next day and so on. And this is how the entire prediction operation is going to work. That's the entire sequence of computation. And you can see how, if you just follow the arrows, something over here is going to influence that prediction, goes back here, influences that prediction. If there's no further input at all, a single input is going to influence the predictions forever, right? I'm just going to read right like this. Yeah, was there a question?
Yes.
Go
So
ahead.
if we look at it like that, if we want to predict for a specific day, that means that we will be going from like infinite day before by
Yes.
taking one input each time to predict. So
Exactly.
is it really good? Like, it's the same problem, like?
Not really, right? So the point is, you can decide on your day 0. So you're going to have to initialize your y minus 1, whatever that might be. And once you initialize the y, the minus 1, from the point at which you begin making your predictions, it's going to continue making predictions into the future, right? The point, there is a memory variable over here. Where are you carrying all the memory? Whoever answered this question. Where does the memory about everything that has had about the past reside? Does anybody want to? In the parameter? Where does the memory reside? In y, right? Everything about the past lives in y. Nothing else is being carried forward. And so now you can generalize this network. You can say that the output depends on not just yesterday's output, but the outputs of several days in the past. And not just today's input, but the past several inputs as well. So you can generalize this. This is called an order KL NARCS network. And where it looks, you are looking at the past KL inputs and the past K outputs, right? Now, NARCS networks are very, very popular. In fact, if you are using large language models, there's some variant of NARCS networks every single time. They were popular for a while, then they went out of fashion, and now they're back. People may not call it the same thing, but they're back. So they're used for predicting weather, they're used for predicting stock markets, for language, right? Now, any phenomenon that has a distinct innovations and input, where there's a trend which can be captured through the outputs, and a distinct input that drives the outputs, can be modeled by a NARCS network. The key thing is that the memory about the past is entirely captured in the output and not in the network, right? Now, this is not a great thing. You'd like the network itself to know what computations it has performed in the past and build on it. and not depend only on the output, right? So what we would like to is to have some component of the network be responsible for memory. And this led to the development of various network architectures where we try to explicitly introduce the notion of a memory variable. And the earliest techniques did something like this. You have a memory unit represented by MT, which is a function of past outputs, past hidden values, past and current inputs, and whatever was in the memory in the past, right? And the hidden variable was a function of the latest, the updated, the hidden variable was a function of the memory itself and the current input, and the output would become a function of the hidden variable. So the memory unit is an extra unit that has been inserted into the scheme to keep track of the operations in the past. So MT is a memory variable generally stored in a memory unit. Now, there were a couple of different variants suggested for this. The first was the so-called Jordan network, proposed by Michael Jordan, who became famous for other works. And this is not the basketballer. This is the guy who does math. And he introduced this notion of a memory unit whose job is to simply retain a running average of past output. So the idea here was that it's not just the immediate output that captures all the information about the past. Every single output that you have seen has some information about all the computation that has happened so far. And so they retain a running average of all of these outputs through this memory unit. And this running average unit is actually fed into the network to make the next prediction. Now, the memory has a fixed structure. It's only the memory unit, all the memory unit is doing is maintaining a running average of outputs. So this means that there's no learnable component of the network where the memory learns how to capture, where the network learns how to capture memory and store it. So it's not really a learned memory behavior. Leaves something to be desired, which led to this development called Ellman networks by Jeffrey Ellman, where he introduced something called a context unit. Now, the context unit basically just cloned the memory, the hidden state of the network. So at each time, the network would perform its computation. Then you just copy the hidden state over into this context unit. And this context unit can retain information about the past. Now, because you're cloning the hidden state, the context unit really does capture some of the information about the inner workings of the network in the past. And so you can see how this makes sure that any operation at any time t, if you just follow the arrows, is going to influence the output forever, right? But then back in the day when this was first proposed, they weren't quite sure how you could train such a network. So the way they did it was, there's a picture missing. They would slice the network at each of these places when they trained it. So this block would become independent of this block, would become independent of this block. So it chopped it off out here and treated every time step with its cloned hidden variable term coming in as one element in a batch. And then you can just do a standard MLP style training, which means that something that happens now doesn't really, an error today doesn't really back propagate. During the forward pass, you're performing all of the computations using past memory through the clone state. But then suppose I find a large error out here, that large error propagates down till here, but because you're slicing this piece off before you update, the information about that error is not being passed backwards. Now again, this is every column is identical to every other column. So this is still a shared parameter network, right? I'm using the same network repeatedly to make predictions at every time. So if I found a large error over here, I'd probably update this connection. And because I'm updating this connection, all of these would get updated too. But then there's no direct flow of information from here to here. Now it may well be that some event actually causes errors in the prediction way out into the future. This is very common in real life. Something that happens today is not going to influence tomorrow, right? You commit a crime today, the police are going to come to your house next year. There are lots of days in between. So if you're just looking at local phenomena, you can't say, oh, based on this, the police came to my house because I had lunch yesterday. It wouldn't be very logical, right? So, I mean, it's a bad example, but it still conveys the story. And so you want the errors to be propagating all the way to the back, and that's not going to happen here. So this was what was called a partially recurrent network, in that there is recurrence going forward. Something that happens today continues to influence predictions into the future. But there's no recurrence going backwards because you're not actually propagating error gradients backwards through time. And so the story so far is as follows. In time series analysis, models must look at past inputs along with current input. Looking at a finite horizon of past inputs gives us a convolutional network. Looking into the infinite past requires recursion. Now, Knox networks recurs by feeding back the output to the input and may feed back a finite horizon of outputs. These simple recurrent networks are the two that we just saw. Jordan networks maintain a running average of outputs in a memory unit. Elman networks store hidden unit values for more than one time instant in a context unit. But this is simple or partially recurrent because the recurrence only happens going forward. But when you're trying to learn the parameters of the network, you're slicing each time instant out. And so errors do not propagate backward into time. They're blocked at the context units. 5 seconds, guys. Pokemon Surskit. Is that the correct pronunciation? Surskit, S-U-R-S-K-I-T. Are you around? Pokemon Surskit. Abhishek Anand. No. Okay. Pokemon Gyarados. What's the answer to the first one? False? Okay, thank you. And Pokemon Magnemite?
Yes.
True. Or what's the answer to the first one? It's true. Okay. Does everybody agree that the first one's false and the second's true? Okay, easy enough, right? So we've looked at two kinds of models. We've agreed that recurrence is required for, we want recurrence within the network for inputs to influence predictions all the way into the future. We've also agreed that it is necessary for inputs to influence predictions all the way into the future. We've looked at two ways that in which, so we've also determined that recurrence can be done in one of two ways. You can actually have the output come back and influence the input, but that sort of stores the entire memory in just the output. You would ideally want the network parameters, the net intermediate variables of the network themselves, to capture information about the past. So we saw two models for recurrence, one of which was the memory unit, but then it really didn't build on the Knox network because it was just using a running average of memory. And then we saw the Elman network, where we were actually using the hidden state for recurrence, but there was no back propagation because you sliced the individual time instance off when you were propagating gradients backwards. So how would you improve on this? Anyone? How would you improve on this? Pokemon Ecans, Mingxan Li. Any suggestion?
I'm not sure.
Does anybody want to take a guess? What was the problem here with this method? Yes, Ben. You were segmenting it, right? So what would be the next obvious thing? Don't segment it, right? So which means that would, you just want to propagate the error back here. But since this is a clone of this guy, do I need to make a clone? I can merge these two, right? And so that's the next obvious step in the proceedings. We get a state space model where now the hidden state of the network itself is dependent on the hidden state at the previous time and the current input. And the output depends on the hidden state. So any of you, any electrical engineers here? Someone who's worked on control systems? No? This must be very familiar if you worked on controls, right? This is a standard state space model. You have a state of the system which keeps evolving, and then observations are dependent on the state. And so here the output y depends on the hidden state, which is recurrent, right? This is called a fully recurrent network because you're not slicing things out. This actually allows errors way out into the future to propagate all the way to the back. So here's what the state space model looks like. A single column of the state space model is this. At any time t, the hidden state is going to be computed based on the hidden state of the previous time and the current input. And the output is computed hidden based on the hidden state. So if you looked at the entire computation, it's going to look like so. You're going to start off at time 0 and make your initial update of the hidden state based on hf minus 1, compute your outputs, and then just repeat the same computation going all the way into the future, right? So what are the parameters of this network? Anyone? How many unique parameters would you be finding for this network? Chetan, well, how many unique parameters would you find? I'm not calling your Pokemon name because you're right here.
You have to learn the weight for like the H minus 1, and then the weight of the input at each.
Right. You can just have to look at this figure, right? You're going to have to learn this weight, and this weight. Is there anything else you want to learn? Anything else here that's maybe required? Somebody want to guess?
Bias?
Can you repeat that? I think you got it, but can you repeat that, please?
I said bias.
So the bias, no. This guy, hf minus 1, what is it, right? At the very initial time, you have to specify hf minus 1. Now this could be just a fixed value, 0, or it could be learned. And then subsequent computations can just be done. So you have, this is the alternate model. You have h of t is a function of the current input and the hidden state of the previous time. The output is a function of just the hidden state, and you need to define h of minus 1 in addition to the parameters comprising the 3 edges. Now, I've just drawn a single green block in the figures representing the hidden state, but the hidden state can be arbitrarily complex. Inside that little green block, you can have all sorts of things, right? So your hidden state, for example, could be something like this, just one single layer of neurons. Now again, observe that an input at time 0 will influence predictions through these arrows all the way to the end of time, right? So this, yes, Chetan.
Would your initial hidden state not just be like an initial guess to what you think it should be? To learn that to get to time.
It is an initial guess. So what is an initial guess? We don't really know, right? So you could just set it to zeros or actually learn what is the optimal way of initializing the network. Right. And so now I could also have something like this where I have 2 hidden layers. Vibha, you want to go wash your face? Okay. And you can have something more crazy like this, something even more crazy like this, pretty much any kind of figure that I can draw, right? The thing is, when I do this, at the end of the day, it sort of collapses to exactly the same kind of structure, namely that I have x of t, which is influencing a hidden state. All we are doing is increasing the complexity of the hidden state. And so in increasing the complexity of the hidden state, you could also be increasing the complexity of the connections through which it's communicating with the hidden state at the previous time. But the general concept still remains the same, right? Although something like this is a bit crazier in that something that's at a higher layer at the previous time could be communicating with a lower layer at the current time. Now, there's nothing saying you should be looking back only one time step, right? I could also be looking back 2 time steps, like so. But if I were looking back 2 time steps, what else do I need to specify over here? Anyone? Yeah.
How many time steps to look back into?
H minus 2, right? Because at the initial time, you're going to know what you need to know what the state was 2 time steps ago. You can make it arbitrarily deep as well. It's still recurrence, right? And the most popular structures are these because they get the most bang for the buck. But honestly speaking, having recurrence going back 2 or 3 time steps in this manner can get you a lot of power. It just makes computation more complicated. Something you could try in your homeworks, by the way. I'd recommend that somebody try. It's not in the write-ups for homework 3, but definitely worth giving it a shot. So now if you actually look at the figures in the textbooks of the past, or even modern textbooks, you're going to see figures of this kind. They give you this crazy impression that this output is being fed right back in and that there's some kind of a loopy structure, but that's not what it really means at all. What this really means is that that's recurrence, right? So a figure like this represents computation of this kind. A figure like this represents computation of this kind. This would be computation of this kind. Again, the point is, in the illustrations, when you see a loopy arrow shown in red, it really means that's a recurrent connection, right? So how do these different connections work now? Easy enough. You can work through the arithmetic. Consider this little this network where you have a single hidden layer, and the hidden layer is recurrent, meaning the hidden layer state at any time feeds into the hidden layer at the next time. So here are all the computations that you'll be performing. Actually, I've written this in scalar form. Let me write this in vector form, but actually, no. First, this hidden state is going to be computed by applying an activation function on the affine function of the input and the hidden state at the previous time. So it would be something like a weighted combination of the input plus a weighted combination of the hidden state at the previous time plus a bias. That's this affine term. And you have an activation function operating on it, right? The output layer is going to be working on a weighted combination of the hidden state at the same time plus a bias. And then you have a different activation applying on it. And most often, in the recurrent hidden state, the activation function that we will use is a tan H for reasons that we will see in the next class. And you can distinguish between 2 kinds of weights. I've written the same thing in vector form. So if you look at the first hidden state, there's an activation function F1, typically a tan H, that's operating on a weighted sum of the current input, the past hidden state, and a bias, right? There are 2 sets of weights over here. This W superscript 1 over here represents what I will call the current weights. The weights corresponding to all the edges that are going straight up. And then this W superscript 1, 1 are what I will call the recurrent weights, the recurrent weights, which correspond to the weights on the horizontal arrows. They are speaking to the same layer at the previous time, right? And similarly, the output now is just going to have it's going to be operating on an affine function of the hidden state at the current time. So these are current weights, and you have an activation that's being applied, which could be, a softmax or just a linear activation if you're making real value predictions. So these are the current weights and the recurrent weights. Recurrent weights are the ones which enable the hidden state to carry information from the past, right? Now something like this, you have the same, if I have a multi-layer hidden state, this is again written in scalar form. Let me write this in vector form, and you can see how this works, right? The hidden state, the first hidden state at any time is obtained by applying an activation function, again typically a 10H, on an affine function of the input and the same hidden state at the previous time. So this is going to be a current weight through this, a recurrent weight which is W11, which is the weights for this connection, and you have an activation. But then the next layer is actually operating on the hidden state at the previous time. So now the current weight actually applies to H1. So this guy here is going to be some activation function, again typically a tan H, of the current weight W superscript 2 applied to the H1 plus W22 applied to the hidden state of the previous time, right? And the output again is as before. So again, you get the idea that at each time, the hidden states themselves can have many layers, and they're going to be communicating with the layers underneath them and with themselves from the past. And the connection that comes in from the past is what is carrying the recurrent information, the information from the past coming in. And so here's an uglier network with similar equations. I won't go through the details, right? Now, so you get the point is you get the idea of recurrence. And the idea of recurrence is that when you have a sequence of inputs, the sequence of inputs is going to be operated on through this recurrent network, where at each time the hidden state is being computed based on the current input, the hidden states at the previous time, and the hidden states at the previous time, and the output is a function of the hidden state at the current time. Now, this, you don't necessarily need to compute an output at every time. The real recurrence, you can ignore what's happening at the output. The real recurrence is the input and how the input is recurrently being processed by the hidden state. And as a result, there are different ways in which a recurrent network can be configured. So let's look at a few. These are pictures I stole off the web, but they're still correct, right? Who did I get these from? From Andrew Karpathy, who's maybe the best person you can find on the web to teach you anything neural networks or anywhere. So the figure to the very left, that's just your standard MLP. Your input, which is processed by the hidden states, and the hidden states are used to compute the output. This is a one-to-one network, right? But then here's something. I can have a single input and no further inputs, right? The recurrent states are just computing all on their own, and then you generate a sequence of outputs. Or I can have the reverse. So this would be, for example, a conventional MLP, something like this. You look at an image, and then you generate its caption. So you're just looking at one input, a snapshot, and then you're generating an entire sequence of words, right? The third one is the opposite. You look at the entire news article to decide that we are unhappy with the Steelers. So you see the entire sequence, and then generate an output, speech recognition, text classification. But then you can also have things like this, where you look at an entire sequence of inputs, and then when the entire sequence of inputs is done, you make a prediction for about the entire sequence. You predict the entire sequence of outputs. Can someone give me an example of where something like this could be applied? By the way, you at the back, the striped shirt, guy at the back, can you just knock on it? Do you mind leaving the class? Because if you're looking at the phone, I don't want you in the class. Or put your phone in the bag. Thank you. Right. So, can you have your name tag out? Please get it out, okay? So can someone give me an example of an instance of the first network? Get your name tag out. Make one. Right? Can someone give me an example of the first one?
So,
Machine translation, right? I look at an entire sequence of English and I generate an entire sequence of French. But until I get to the last word, I can't really decide. I mean, if you've done any translation from German, you know that the verb comes at the very end. You don't know if someone loves someone or someone hates someone till you read the last word, right? So, and then of course, the last one where you might be doing something like predicting the stock market, where each day you're going to be making predictions, right? So here is the story so far. Time series analysis must consider past inputs along with current input, and looking into the past, infinite past, requires recursion. Knox networks achieve this by feeding back the output to the input. Simple recurrent networks maintain separate memory or context units to retain some information about the past. But during the learning, the current era doesn't influence the past. These are the simple recurrent networks, the Jordan network, the Elman network. Fully recurrent networks are typically state space models where they retain information about the past through the recurrent hidden state. The initial values of the hidden state are often learnable parameters, but you can also just specify them as zeros. And state space models have this characteristic that they enable current error to go all the way back into the past, right? So, any questions?
What is the hidden state? Like, what's inside it?
What is inside the hidden state? You're wearing a mask. I didn't know you were speaking. I'm sorry. But we really don't know. It's just a recurrent state. It's no different from the hidden state of any multi-layer perceptron. What is the question, Chetna?
In some of the previous you had many to one or something. How did you make one hidden state turn to like multiple hidden states when you only had a single?
Okay, just consider this thing, right? Suppose I just give you this input and all the rest of them are zero. What would it be doing?
You would learn just the weight from.
So we'd be learning all of the weights, right? Imagine all I ever gave you was training sequences where I had a single input and all the rest were zeros. You can still learn recurrent weights, right? Nothing changes. There was a question on Zoom?
yeah, I had a question about the backpropagation part, as it's the same unit which is taking input like recurrent time, and it's not like convolutional neural network where we have many layers and we can backpropagate for each layers and each parameters. So everything we have here is the previous output and the next output. But how can we
That's exactly,
backpropagate?
you're predicting the next 10 minutes of the lecture. So just hang on.
Oh,
That was a good question, right? And the question is, how do you train these networks? Now, the first thing you must observe that every column is identical to every other column over here, right? So this is a shared parameter network. Everybody see that, right? Now, given that this is a shared parameter network, regardless, this is really just an MLP, is it not? Can anybody tell me how this is an MLP? If I just redraw it like so, I can just redraw it. I can have x0. This is h of minus 1. I just do this on the side, and this is y, let me call this y3. This looks like an MLP, correct? Except that it's generating outputs at each time. Does this look like an MLP? Just because I redraw it on the side. I flip my head sideways, this is what our MLP looks like. If you were training this network, which direction would you be propagating the errors? We're going to go from the top and you're going to go against the arrows, right? So the derivatives are going to be going backwards, which is why we call it back propagation through time. You're pushing the derivatives backwards through time. So here's how the training happens. You're going to be given a collection of inputs and outputs, except because these are series models, you're going to be given a collection of input sequences and output sequences, right? So X's and D's, where D is the desired sequence of inputs and X is the desired outputs and the D is the desired sequence of inputs. Now the network, in response to the input, is going to make a sequence of outputs as predictions. And so what you would really be doing, this is the entire unrolled computation. This is a giant parameter network where all columns are identical and share parameters. Network parameters can be trained via gradient descent using shared parameter gradient descent rules, exactly as before, right? Because we know that the actual derivative that I will use to update these weights is going to be the sum of the derivatives at each of these locations. This was the shared parameter rule. Remember that if you have a whole bunch of connections that share the same parameter value, then you're going to just add all of their derivatives up. And so we can just use the shared parameter derivative rules to learn the parameters of the network. And like any other network, you're going to have a forward pass where the input goes into the network and it makes predictions at every time. So the forward pass pseudocode, for those who prefer to think in terms of code, at the we can think of the 0th hidden layer as just the input, right? At each time, you're going through all of the layers bottom to top. The affine value at each time is going to be an affine combination of affine function of the hidden layer at the same time, one layer below, the hidden layer at the previous time, the hidden state value at the same layer at the previous time in the bias, and then you apply an activation. So that's just showing you the computation going up. And then finally, of course, you have the output layer performing its computations from the uppermost hidden layer, easy enough. And now the derivatives must go backwards from the end to the beginning. That's why it's back propagation through time. Now, just to make things a little more explicit, instead of having two arrows coming into the boxes, one from the bottom, one from the side, which makes things a little bit confusing, at least to me, I'm going to redraw things in this manner, okay? And now the network is going to have make a sequence of predictions, one at each time, correct? And then it's going to have a sequence of desired predictions, correct? You would be computing the divergence between the actual sequence of outputs and the desired sequence of outputs. So the divergence is not the divergence between individual predictions and their corresponding predictions. The divergence is going to be the divergence between the output sequence and the desired sequence. So what is the difference? Why would this matter? Yes?
Can't really do fast training because you need the whole series of inputs.
That's one thing, but the more important thing is you may not have a one-to-one correspondence, right? Very simple. For example, if I'm doing something like machine translation, the network may produce a sequence of 8 words, but your ideal translation is 6 words. How do you find the one-to-one correspondence? More often than not, there is no correspondence, right? So you really cannot be computing, you can't break this down into the standard problem where at each time there's a prediction and a desired prediction. It's that you have to always think of it as the divergence between two sequences. And this causes a problem because very often the kinds of divergences, the errors that you compute between two sequences are not differentiable. Because how did you compute the error in homework 1, right? Oh, actually homework 1, you'll see this in homework 3. You'd be looking at Levenstein distance, which computes string edit measures between strings and strings, which can be of different lengths. This is not differentiable, right? So what would the solution to that be? We'll get to this in subsequent classes. Would anybody? This is a slightly Socratic question, but slightly, I know the answer. It's not truly Socratic, but how would you go about it? When I give you this divergence measure, which is looking at, which cannot be written, which is not really based on a one-to-one correspondence between the actual and desired outputs. You can't really use subgradients. I don't expect you to know the answer, but what we will do is to try to somehow manipulate it so that it begins to look like a divergence that has one-to-one correspondence. Because without it, computing derivatives becomes really hard. And in fact, it's impossible. And training becomes hard, right? But most generally, this is not just the sum of divergences at individual times. This is something that you must remember, okay? And so if I were to just write the problem down, the network makes a sequence of predictions, one prediction at each time. So yi of t is going to be the ith output. At each time, there's a vector of outputs, right? And at time t. And now I have, so y of t is the output at time t. I'm just introducing some notation for this particular picture, but this will generalize to any kind of network. So at each layer, you're first going to compute an affine value. This z is going to be a function of what? The input here and the output of the previous layer, right? That goes through the activation, is going to compute h of t over here, from which I compute an affine term z here, which goes through an activation and computes an output y. And this sequence of y's is compared against the target output, and then you get a divergence. Now, the first thing I'm going to assume is, and here are all the parameters. You have the current parameters, which correspond to the vertical arrows, and then you have the recurrent parameters, which correspond to the horizontal arrows, right? The recurrent parameters are indicated by the double superscript, W11 in this case. Now, in order for back propagation to work, you need to be able to compute the derivative of the divergence with respect to every single output, because that's the derivative that you're going to be propagating backwards. So regardless of how you define the divergence, eventually you're going to need the derivative of the divergence with respect to yt minus y, yt minus 2, all the way to y0. If you do not have those derivatives, there's no derivative to back propagate. So a lot of the work that we will do in the coming classes is on figuring out how to manipulate our divergence so that you can actually compute those instant-wise derivatives, right? And so I'm going to assume that I have the derivative of the divergence with respect to every single output. Now, before this, we're going to use two rules for our derivative computation. Is there an eraser here? I don't need one. So you guys are going to help me write out the back propagation rules, right? Now, let's say I have yi minus 1. This is using, in my case, a weight w. It's being put through a so the affine term is z. This generates output by I, and there's some downstream process from which I get a loss. So if I assume that I have the derivative of the divergence with respect to the output, right? Given. Then if I were performing back propagation, what is the next derivative I would compute? Again, I need derivative, this is Pokemon Heracross. What's the next derivative I would compute? Heracross, Caleb Way? No? Okay. Pokemon Magmar? Pokemon Magmar? Are you around? Yes, is that you? Okay. What is the next derivative I'd compute? I have the derivative at this point, which is the loss with respect to yi, right? So what is if I'm computing derivatives backward, what is the next thing I'd compute? This is going to be the derivative of dy. I'm speaking in terms of vectors, right? I'm back propagating derivatives. Am I going to be computing dy over dz? I need the derivative of the loss with respect to z, do I not? Right. So what is this going to be? This is going to be the derivative of the loss with respect to yi. Continue. What is that? Anybody? So this is going to be, if I write it in vector format, that's just the Jacobian, correct? So this is going to be, but I'll write it as yi over z, right? And then having done this, so I need another Pokemon Golem, that would be you, right? What is the next derivative I compute?
dl with y raised to power minus to I minus 1.
Yeah, that's going to be?
dl with respect to zi multiplied by w.
Perfect, right? Lovely. And yes, Chetan?
Is the gradient of y, like that second term that you wrote there, the one to the right, is that just the derivative of the function f?
Yeah, that's just a Jacobian, right? And then what else do I need to compute here? I need another Pokemon. So Pokemon Sunflora. I don't see her here. So Pokemon Sunflora. What's the next derivative I'd compute? Okay. Yes, go ahead. All right. Pokemon Corsola, Tebujiang. Guys.
Sorry, I
Yeah,
do not.
so, yeah. What is the next one I would compute? The next derivative. Or does somebody want to help him? What's missing?
I think, yeah. We have to calculate the derivative of the Lagranges with respect to the weight.
Perfect, right? And what is that going to be?
The input.
Input times what? Anybody else? Derivative of the loss with respect to z, right? So great. You guys actually remember this stuff. I'm very thankful. You know. So yes, this was easy, right? We are going to use these three sets of rules. And now look at the second figure. The second figure is not really anything more complicated than that yi is now being fed out to two different connections, okay? So in this case, I have yi going here to give me, say, let me just call this z1 and z2 for whatever. And then I have their own activations, and all of these contribute to the loss. So then what is the derivative of the loss with respect to y? I'll call this yi. What is this going to be? Anyone? You're going to be? I'm going to be summing these two, right? So which is going to be the derivative of the loss with respect to z1 times w1, right? Plus the derivative of the loss with respect to z2 times w. I call these w1 and w. So everybody clear about what we are talking about over here, right? Very simple rules. Not too complicated. You're all familiar with this. But let's see how this works here. So I'm going to start off, I'm back propagating through time. So I'm going to start at the end. So I'm going to assume that I have the derivative with respect to yt. So if I'm back propagating, what is the next derivative I'll compute? So what is the next derivative I'll compute for Pokemon Ninjask? Yeah. So I have the derivative with respect to yt. What is the next one I'll compute?
with
think you're
respect
saying
to
the right
z.
thing. So I'm going to compute it here, right? So that would be? Isn't that going to be following this rule here? Correct? So what would that be? It's staring you in the face. Somebody else want to help him?
Respect to the outcome.
No, so you're going to be, you have the derivative with respect to the output. So the next thing you'll be computing is the derivative with respect to the affine term, which is the derivative for the output multiplied by the, what was it? The Jacobian, right? The derivative of the activation function itself. Make sense, Colton? I know, it's hard to keep track. I don't blame you for this. Yeah, there's a lot of information coming your way. I don't expect everybody to get everything, but it helps to jog you guys. Pokemon Diglett, what's the next derivative at compute? The next arrow down, so what would that be? Go ahead. So I'm going to be computing the derivative for the z over here. And what is that? I'd be using one of these formulae, would I not? I'd be using this one. The derivative for z, y times what? The w, correct? And what else would I need to compute? Next one. Pokemon Hariyama. So what is the next thing I'd compute? Okay, anybody else want to help here? Go ahead. Pokemon Psyduck. What kind of strange names are these? So what, Pokemon Psyduck.
Yes.
What is the next derivative you'd compute? Anyone else?
With respect to the hidden state.
With respect to the weights, you're forgetting the weights, right? There's a third thing that we did not. Anytime you have this connection, you're computing the derivative with respect to the affine term, the previous input, and the weights. Each connection is going to give you 3 derivatives, right? And so that's going to be just the input value here, ht, times the derivative with respect to z, correct? If I continue this trend, what is the next derivative I'd compute?
Like the hidden state on the previous layer.
The hidden state of the previous layer, right? That's simply going to be multiplying the derivative for h with respect to what, Aryan?
The derivative with respect to z times
the input? I'm trying to compute the derivative for z. He's daydreaming. I just caught him daydreaming. That's okay. But still, what would he be multiplying it with? With a Jacobian, correct? And then next? That's going to be the derivative for the weights, which is going to be x times the derivative is with respect to z. So we are done with one column. There's one more derivative to compute. Which one is that? 2 more derivatives. So Fortress, what's the next derivative at compute? Oliver Zhang.
The derivative for the previous name?
The derivative for the hidden state, which one? Okay, let me just help you guys, right? I can compute the derivative with respect to the recurrent connection, right? And I have to write derivative, that's simply going to be this hidden state times the derivative here. So we are good. But then when then I'm done with this time step, then I have to go backward. Here's the thing. I cannot yet compute the derivative with respect to the z. Why? Because there's another connection coming down from the top. And so things get interesting here. First, I'm going to assume that I have a derivative with respect to yt minus 1. Okay? I pass it back. I multiply that derivative by the Jacobian. And then I'm going to get the derivative with respect to the z at that time. And then I can go down And here's the thing, when I compute the derivative with respect to the output of the hidden layer there, that output is going two ways. One is going up, one is going to the side, right? And so based on this rule over here, it's going to be the derivative of the sum of two terms, right? One coming in from the top and coming in from the side. Everybody with me here? It's easy, right? And so then this is one, but here's the other diff change we're going to make. When I compute the derivative with respect to this weight, the derivative for the weight is going to be the local derivative, which is this h times the derivative coming down from here at this point, which is going to be ht minus 1 times the derivative with respect to z2 at time t minus 1. But this derivative is going to actually add to the derivative that I already computed out here, because all of these columns are identical, right? And so we're going to be using shared parameter rules. At each column, I'm going to get a derivative, and I'm going to add it to what was already computed in the past. That makes sense to everybody? Guys on Zoom, that makes sense to you? Someone say yes, please, for my sake.
Yes. Yes.
Yes, sir.
Appreciate it. And so, and then I can move on down. I have the derivative with respect to h. I can just multiply that by the Jacobian, get the derivative with respect to the input. But then the same thing happens again, right? When I compute the derivative with respect to this weight, what is it going to be? Anybody? What is the local term? It's going to be the input times the derivative here, right? And that's going to sum to what was already there, because you computed the same derivative at the next time instant. And so you just be doing a plus equals, because you already computed one derivative at the next time, xt minus 1 times the derivative with respect to the z. Right? You can see how this gets incremented. There's one more derivative, which is that, the horizontal connection, right? And for the weights for the horizontal connection, you have the same issue. I can say that I'm going to compute a local derivative, which is the input ht minus 2 times the derivative with respect to the next z that it feeds to. But this actually increments what was already computed. Yes, Stephen.
So just to verify, because each column here is a shared parameter network with multiple columns, every vertical derivative we calculate with respect to the weights is added on to.
Exactly. Also for the horizontal weights. Same thing, right? But besides, all we've done is taken your standard back propagation rules and accounted for the fact that these parameters are shared, right? And so I can use this thing going all the way back, the same sequence of derivative rules. I can even update my hf minus 1, right? If I want to learn it. So here's the complete set of equations. I'm running out of time, so I'll rush through. But at each time, you're going to start at the end and you're going to go down. And each time you'd have the derivative here. You're going to use that to compute the derivative here. Then you compute the derivative with respect to this weight, which is added to the derivatives you've already computed. Then you would compute the derivative with respect to the affine term, which is going to be the sum of two terms here, because there are derivatives coming in vertically and horizontally. Pass that down to compute the derivative here. Then you compute the derivative with respect to this weight, again, which increments. And then you're going to compute derivatives with respect to the recurrent weight, which also increments. And you can just keep going backwards. So I have some pseudocode over here that I will skip, right? And this can be generalized to pretty much any architecture. I'll give you a very short 30-second poll, because there's one more topic to finish, and I have 5 minutes. I'll go over a couple of. Okay, guys, derivative Stantler. What's the answer to the first question? Pokemon. So Pokemon, the derivatives. Okay. Pokemon Stantler. What's the answer? Yes, what's the answer to the first question?
I said true.
True. Does everybody agree that it's true? The first one. Would you be updating the network after each vector? No. You have to process the entire sequence because now inputs are entire sequences, correct? Pokemon Doug Trio. So Doug Trio, I don't know if I pronounced it right. Okay. Pokemon Pinnacle. What is the answer to the second one? Pineco, Pinnacle. No? Okay. And Pokemon Ponyta. Pokemon Ponyta. What's the answer to the second one?
All of them.
All of them. Okay. Does everybody agree that all of the statements here are true? No. Okay. Only the second one is true, right? The divergence we minimize is the sum of divergences for individual inputs? No, right? It's just that the divergence must have a derivative with respect to the individual outputs, but the divergence itself doesn't have to be the sum of local divergences. And the divergence is the difference between the actual sequence of outputs and the targeted sequence of outputs. So questions? No? We're going to move on to the last topic, which should take 10 minutes. I'm going to finish it in 7. I'll run over by 3 minutes, right? Now, in all of this, we've assumed that the information flows left to right, starting from the beginning, going to the end. But then think about it. If the current carries information about the future carries information about the present. So if I could see the entire input before making my predictions, then ideally, I should also be considering the future, right? So in that case, you might assume that the correct thing for you to be doing is something like this, where I have X, I have H, and then I have my Y, and I should be looking at both the left and the right? There is continuity. If I'm looking at part of speech tagging, for example, what part of speech a current word is I'm informed both by previous words and what follows. But would a network of this kind work? Can you have something of this kind where you have information coming from left and right, both left and right?
No, it's cyclic, right?
Why? Okay, why not? I'll tell you why, right? If I just expand it out, you're going to have connections like this. For any given sequence, things are going to be going back and forth and back and forth and back and forth. This is not going to be possible, right? Yet, we want information coming both from the left and from the right. So how would you solve that? Anyone? You have one layer going left to right and another layer going right to left. And so what we just do is this. We have this lovely paper called by Paliwal back in Shuster and Paliwal, that's in 1997. Here's the figure from their paper, but here's what we really do. Within each layer, you have two subcomponents, one a left to right component, which processes inputs left to right. The other one processes the inputs right to left. Each of them generates its own output. The actual output of the layer is simply going to be the combination of the two, which could typically be, you could add it or just concatenate the two outputs, right? So here, this left to right layer is generating the forward hidden values. The right to left layer is generating the backward hidden values. The overall hidden state is basically just the concatenation of the two hidden states. That makes sense, right? And so this block can be attached in. Again, each of these things can be arbitrarily complex, although we typically like to keep them simple. So these guys could be, more complicated. You don't want to complicate them too much. But the idea is each block now is looking at the input both right to left and left to right. And so as you go through the layers, because the hidden state is always considering both the future and the past, over several layers, the predictions begin to consider futures and pasts. Now, there's one poll, then we'll just go through backprop in a couple of minutes, and then we'll be done. Since there is only one question, so stop here. You have 5 seconds, guys. There's only one question. Pokemon matchup. That is a Pokemon. That's Alice. Pokemon matchup is missing. Pokemon Oddish. I know. That's Rohit. Pokemon Oddish, are you around?
Yeah, I'm here.
Okay. So what's the answer?
False.
False. Why?
Because he shouldn't be using like future data.
You should not be
to make
using the
his
future.
prediction.
The future is not available, right? Perfect. So now again, in terms of code, it's very simple. I can just going right to left is the same, can be done using the same code that you use for going left to right. You just flip the input and pass it, right? And pass it along with the parameters. Anyway, take a look at the code. How does backprop work? So backprop is simple. Now I have at any layer, I have an input x or ht, you know, I'll call this h my t minus, L minus 1 for the previous layer, right? Now this is going in, and I'm getting the forward outputs, FHF, and I'm getting the backward outputs, HB, and these are concatenated, so I get HB concatenated with HF, right? I'm just drawing it horizontally, but they'll be vertical. Now when I'm computing my derivatives backwards, I'm going to get the derivative with respect to this concatenated vector. So now when I'm coming back, I'd have a derivative which is with respect to HB and HF. This portion I'm going to slice off and pass this way. This portion I'm going to slice off and pass through the forward network. That makes sense? Right? And so I would have the back propagation here. I'm going to be slicing off the forward portion of the derivative and passing it backward through the network using regular BPTT. I'd be slicing off the backward portion and passing it forward through the reverse computation, because again the derivatives go against the arrows, right? Now at each time when I pass this information back, this derivative which comes this way is going to give me a derivative with respect to h. The derivative which goes through this, which is also going to give me a derivative with respect to h. What would I do with those two? I would sum them up, right? So very simple. And so both of them are just going to, the forward and backward derivatives are just going to get summed up. Very simple, right? I have pseudocode. I'll skip that. I said 3 minutes, so we're 3 minutes over. So to summarize, recurrent networks look into the infinite path through a state space framework, hidden states that recurs on themselves. Training recurrent networks requires defining a divergence between the actual and desired output sequences. Back propagating gradients over the entire must be done over the entire chain of recursion, and also the gradients must be pooled with respect to the individual parameters, because these are really shared parameter networks. Bidirectional networks analyze data both ways, begin to end and end to beginning within each layer. And in these networks, backprop must follow the chain of recursion separately in the forward and reverse nets. We'll stop here. In the next class, we just sort of quickly summarized what recurrent networks are. We'll look at limitations and how we can, of this basic framework, and mechanisms we can use to overcome these limitations. Right? Thank you.